So we are presently at Nödinge Kyrka, Nödinge Church. It's a very lovely one, almost 300 years old, and it's exactly 200 years before quantum mechanics, give or take a couple of months, which is in itself quite extraordinary, I'd say. And let's find us a spot here for the lecture. It should be not a grave, and this is a grave. What does it say? I can't really read it out. I'll go down here, put on pause, sorry. See here, it's a lovely bench here, and I need to be faced against the sun and hopefully with some, oh, quite bright here. Standing with the sun in my eyes, but it will be cloudy soon. Hello and most welcome to Heidegger 990. We're just a measly 10 lectures from the 1000. That is nothing but extraordinary, and I'm really happy that I could choose any article, even such a neutral subject as face recognition, and still see that that leads into the same direction as everything else. So this is what I felt recently, the event of unidirectionality in the lecture series, how they are all adding up synergetically. Synergetic means that the effect of each thing that we've gone through or done will add to the force. And since there is almost 1,000 now, that's a lot of hours of studying, researching and understanding. And that makes for a foundation that is not excluding, like the left hemisphere I mentioned before. It is inclusive. Inclusive knowledge means that you don't take antonyms in this simplified, sloppy, arbitrary way, saying that there is a polarity between good and bad, right or wrong, true or false. All those simple tunes. And my favorite example will still remain the critical, the object of much criticism, the Yale School of Literary Criticism, vaguely inspired by Derrida, shaming his memory with his mechanical idea of antonyms, contradictions, difference and sameness. It's a pure shame. But we also need to understand, I don't think Derrida would be angry, the level of knowledge you have, it can't be expanded in the modern academical situation. Actually, educational system is built to preserve that little knowledge that we had when we started school. And this has been shown in several experiments and research objects. Some of them you can find in reference in the Matter of Things, the most expanded research foundation to be found in this universe when it comes to things with connection to knowing, epistemology, neuroscience, science of cognition, well, the whole lot, everything. And it also shows that we lost a lot of knowledge. This has been a closure a stopping point of knowledge that has made us unknowable. And when I use the word knowledge, I mean it in the normal sense. I don't mean a particular sort of knowledge, abstract knowledge, wisdom or anything like that. I mean knowledge. Knowledge is just knowledge. And I would say the educational system gives none to even negative knowledge. The little you have, you lose in the renaming process. Something that is pointed out mostly by Robert Magliola, but also Rodolphe Gachet, and this is also, of course, the very project of Derrida. You could actually say that the deconstruction shows stupidity, but not on behalf of only the writer, but writer and reader together. This is this overgeneralization that is ignorance. Ignorance cannot be anything other than overgeneralization, universalism. Less complexity means less world and less of you. Less of the self, less of self-reflection, and less of complicated world out here. And I mean literally out here, in the shared reality. And the academical stance is, as Edward de Bono pointed out, the idea of a communal world. But we know the world is not shared, not on that level. Sharedness only comes with a high complexity. Otherwise, we just use the same word, but we don't refer to anything. Reference can only be if you actively project. That means that most people don't have access to reality. This is the unjust situation in modern society. To make everything a bit more harsh, we have gained when it comes to economy, food, commodities, health, other stuff, but we lost the most important. We lost knowledge. There is no connection whatsoever in between these things. The gain in food, technology and all that has not caused the lack in knowledge. And this is once more a very common conclusion from so many philosophers, so many thinkers. Yes, they happen at the same time. There is a connection, but it's not causal. The mode we take for our thinking happened to be technology, but it didn't have to be that way. It is not the modern times in itself that cause this misery we're suffering from. And that is, I think, the most positive I ever thought in my life. Because how many authors, philosophers, professors I met, people I met, haven't given up. Maybe not in words, but even more fearsome in action, in passivity. And there are complete philosophies that are based on giving up, like the philosophy of Jean-Paul Sartre, Camus, and loads more. I would say all analytical philosophy is giving up all prospect of knowing and just be a ridiculed person, living your life in shame, playing word games, renaming everything. But this shame is all there is, you think. That is not the case. The modern times doesn't have to be the apocalypse. Modern times isn't the end of the world. Not at all. It's actually the starting point of a descendant that's been going on for 2,500 years. It needed maybe, that's just my guess, I have no idea, needed maybe to be drawn to its conclusion. But what I do know it was needed was the understanding coming from quantum mechanics. This church in front of me, which I will zoom in on afterwards, is 200 years after the event of quantum mechanics. And from that point of perspective, I'm really glad I wasn't anywhere beyond that point, in between where the church was built or even earlier, until quantum mechanics. I'm incredibly happy I was born afterwards. And that is the biggest gift of modernity. And that is a gift that nobody knows about and therefore cannot use. This is why we are here, to change that. It would be a shame that humanity ceased to exist without even knowing what possibilities were ahead. But let's continue with this most interesting article from Chanaka, Justin Kantner and Mamie Bartlett. We were just getting into this even more interesting non-Euclidean phase space and Krumm-Hansel's distance density hypothesis. The foregoing results, the things I mentioned in 989, emphasize an important distinction between physical similarity and psychological similarity in phase perception. Phases that are physically equivalent to each other, as measured by their Euclidean distance in phase space, are not necessarily perceived as psychologically equivalent. In our work, we found that the atypical phase, located in a sparser region of phase space with fewer and more distant neighbors, exerts more influence on the morph than the typical phase situated in a densely populated region with many close-by neighbors. The main message of the atypicality findings is that the surrounding category context in which the phases are found contributes to the perceived similarity. Krumm-Hansel's distance density hypothesis provides a parsimonious account of how perceived similarity is affected by physical and category factors. In her approach, similarity is determined by two components. One, the interpoint distance between two exemplars. Two, the spatial density of representation surrounding the exemplars. As applied to phases and phase space, these independent contributions are conceptualized in the equation below. Similarity phase 1 / phase 2 equals d phase 1 point phase 2 plus alpha delta phase 1 plus beta delta phase 2, where the psychological similarity is calculated based on the Euclidean distance between phase 1 and phase 2, that is the trajectories according to Euclidean space. And the spatial density of exemplars surrounding phase 1 delta d phase 1 and phase 2 delta d phase 2, and the relative weights alpha and beta assigned to those densities. Density delta is calculated as the summed difference between the target exemplar and all exemplars in the stimulus domain, such that neighbors will have a larger impact on density than far neighbors. Near neighbors will have a larger impact on density than far neighbors. The distance density hypothesis predicts that if two pairs of phases are equivalent to one another in their Euclidean distance d, the pair located in the sparser, less dense region of the phase space will be perceptually more similar to each other than the pair situated in the dense region. Sorry, I need to take my jacket off. The morphing evidence confirms this prediction, although the 50-50 morph is equidistant from the atypical and typical phase in similarity space. Subjects judge the morph phase as bearing stronger resemblance to the atypical parent than the typical phase. Let's now get into attractor fields, phase spaces, and recognition. To account for the atypicality bias, we conceptualize phase representations as attractor fields. Now it's starting to sound really interesting. According to this scheme, memory representations such as familiar faces form stable points in the phase space that carve valleys or basins in its landscape. In recognition, analogous to a raindrop moving downhill to minimize its gravitational energy, the to be recognized phase stimulus decreases its computational energy by following the path that leads to the nearest attractor basin in representational space. This is actually the playground mentioned by De Bono. I think somebody copied somebody. Following this approach, the stimulus need not to be a perfect fit with its underlying representation, only a close enough approximation to fall within the boundaries of the attractor field's basin. The potential activation of any given representation will therefore be directly proportional to the size or span of its attractor field, e.g., representations with larger attractor fields will capture a broader range of stimulus inputs. The attractor basins of visually similar faces are spatially close together in phase space, whereas faces that are distinct are far apart. The size of the attractor basin determines its influence on phase space inputs. Phase representations with relatively larger attractor fields exert a broad influence on phase space and have the potential to capture phase inputs processes. Representations with smaller attractor fields have a more limited influence over phase inputs. As shown in figure 4, the Euclidean relationships between phases are preserved in the model where the morph phase is shown as being equidistant from its typical and atypical parent phases. However, the atypicality bias is the result of the broader attractor field of the atypical phase, whose influence extends over a greater region of phase space. Thus, a 50-50 morph that is situated between a typical and atypical parent phase is more likely to fall into the basin of the atypical parent. As mentioned above, the attractor influence on the atypical parent extended to about 37/63% boundary in one of our experiments, suggesting a point of so-called subjective equality where a morph is equally likely to categorize as more similar to its typical parent or its atypical parent. Next paragraph. atypicality bias for non-face objects. So it was not all about faces, as I said in the beginning. There has been considerable debate as to whether the cognitive processes and neural substrates for face recognition are specific to faces, or whether these processes are employed in the recognition of other expert objects. A related question is whether the organization of face representations in face space significantly differs from the organization of objects in object space. Structurally, all faces share the same internal features, i.e., eyes, nose and mouth, arranged in a similar spatial configuration, i.e., the eyes are above the nose, which is above the mouth. Therefore, recognition of an individual face depends on the fine-tuned discrimination of its facial features and their spatial configuration. If the typicality effect is dependent on the arrangement of face representations in memory at this subordinate level of visual analysis, it is plausible that a typicality effect may be exclusive to faces. Although most objects, e.g. chair, bird, car, are fastest to be recognized at the basic level of categorization, objects are identifiable at the specific subordinate level, e.g. rocking chair, sparrow, Volkswagen, on the basis of their structural properties. There is sufficient structural variation within an object category such that some members are regarded as bearing a stronger resemblance to the prototypical category shape than other members. The structural typicality is reflected in category responses, where the typical exemplars, e.g. robin, sparrow, are faster to verify as category members, e.g. bird, than less typical exemplars, e.g. penguins, ostriches. Hence, the grain of resolution is sufficient to arrange non-face objects in a similarity space that is equivalent to faces. Isn't that interesting? Moreover, the organization of object spaces may follow a similar pattern of distribution as faces, where there is a higher density of typical objects located at the origin of the space and a sparser density of atypical objects at the periphery. To assess the structure of non-face object spaces, typically ratings were collected for the car and bird exemplars to determine the typical and atypical members of these categories. The typical and atypical exemplars were then morphed together. Here we have this. A naive group of participants judge whether the morphed object more closely resembles the atypical object parent or the typical object parent. The prediction was that if the typicality effect is special to faces, participants should be just as likely to judge the bird or the automobile morph more similar to its typical or atypical parent. On the other hand, if perception of objects like faces is influenced by structural typicality, participants should demonstrate an atypicality bias for the birds and automobiles. Experiment 3 found a significant atypicality bias for both birds and cars, extending the phenomena to non-face objects. These findings indicate that the phenomenon to non-face objects This findings indicates that the notion of similarity space applies to birds and cars, and presumably to many other objects classes beyond faces, and suggests that the attractor field model is applicable to non-face objects classes in which a given exemplar may be placed along a continuum of typicality. Paragraph on page 147, acquisition of the atypicality bias. How do atypical exemplars come to attract a wider range of inputs than typical exemplars? The dynamic systems approach was intuitively appealing to us for several reasons. First, it stresses the qualities of the time-dependent, ever-changing representational states of perceptual system that respond spontaneously to the environment inputs. Second, dynamic systems are also stable in that their behaviors are consistent and predictable, and flexible in that they can accommodate and change in response to new learning experiences. This characterization seems well suited to describe the face recognition system that is constantly warped and molded to encode and incorporate new face memories. The third, dynamic systems preserve the physical and psychological properties of face space. Proposed that the physical structure of items alone cannot drive the atypicality bias because their distinctiveness is a function of their physical relationship to other category members. Until the category structure is learned, then there should be little or no basis for perceiving certain items as less typical than others. Kantner and Tanaka tested the hypothesis that the atypicality bias emerges only after category learning has occurred, because natural categories such as those used in previous studies of the atypicality bias are known to participants from everyday experience. Kantner and Tanaka created artificial stimuli called blobs, whose category structures could be learned with an experimental session. Each blob category was formed around a central prototype. Typical category exemplars were created by making small deviations on the prototype, while atypical members were composed of larger deviations. Each category consists of 4 typical and 4 atypical exemplars, thus equating frequency across levels of typicality and varying only structural atypicality. Parenthesis, in natural categories, by contrast, frequency and typicality are often confounded. Pilot testing using the preference task described above established 2 blob categories eliciting a statistically negligible level of bias. In order to test the effects of learning on the atypicality bias, Kantner and Tanaka gave a preference task before and after participants trained to categorize members of the 2 categories to criterion Experiment 1. Consistent with the hypothesis, participants showed a small, non-significant atypicality bias, 52%, before category training, but a significant post-training bias, 58%, that was consistent in magnitude with those of experiments using natural categories. In experiment 2, Kanter and Tanaka demonstrated that category training per se is not necessary to induce an atypicality bias within an experimental session. They replaced the training phase in experiment 1 with a simple pleasantness rating task and observed similar results. A small, non-significant atypicality basis, 53% before ratings task, and a significant atypicality bias after, nearly 60%, just because of giving value to pleasantness, what you prefer to look at. This result suggests that participants do not need to be engaged in an explicit categorizing task to apprehend the normative appearance of members within the category, a finding consistent with past research on implicit category learning. Further, they suggest that this form of learning is sufficient to produce an atypicality bias. Next paragraph. A developmental test of the atypicality effect for faces and objects. The finding that the atypicality bias can be shown to accrue with experience using artificial stimuli raises a related hypothesis concerning the development trajectory of the bias. Predicted that children who have not gained sufficient experience with natural categories to possess a fully formed sense of associated category structures should show a diminished or non-existent bias in perceiving members of those categories. Tanaka et al. Tested this hypothesis by presenting faces, birds and cars in a preference task to children aged 3 to 4, 5 to 6, 7 to 8, 9 to 10, and 11 to 12, as well as college-aged adults. Surprisingly, they found a substantial atypicality bias for faces and birds that was statistically invariant across age groups. Wow! Although the bias was stronger for birds, 71%, and for faces, 63%, both biases were evident from the earliest age group tested. An additional unexpected finding concerned the car stimuli, which did not produce an atypicality bias in any other age group. Speculate that their car stimuli, normed in 1997, may not have conformed to current standards of typicality. The bird and face results, however, suggest that the mental representation of these category structures is well established even in very young children. And now we go into the very modeling of the attractor fields. And this is how all perception and knowledging is structured. So this is extraordinarily interesting. Modeling attractor fields, next paragraph. Can the prediction of the distance density hypothesis be tested in a neural network? In previous simulations, neural networks have been applied to study character recognition and atypicality effects in face recognition processes. Connectionist implementation has been shown to preserve the Euclidean properties of face space, where structurally similar faces are located closer together in face space, and structurally dissimilar faces are farther apart. In this approach, the features of a face, such as its outline, internal features, and spatial configuration are abstractly represented as feature units in a phase vector. The similarity between any two phase vectors can be expressed by the angle of the dot product such that similar faces will form a relatively small angle and dissimilar faces will have a relatively large angle. As a test of the atypicality bias, constructed a neural model composed of 3 layers. First, a 10-unit input layer and a 5-unit middle hidden layer and a 4-unit output layer. The typical vectors were constructed such that they differed from each other by 2 feature units, whereas the one atypical vector differed from the typical vectors by 6 feature units. By virtue of the vector structures, the typical vectors are located nearer to the original phase space, whereas the atypical vector is located further away from the origin. In the simulation, the typical and atypical feature vectors provide the inputs to the model, with each vector associated with a unique unit at the output. Training continued for 10 epochs. After learning, morph vectors were created by averaging the values of the atypical phase vectors and the values of the typical phase vectors. For example, the feature of typical phase vector and atypical phase vector were averaged to produce the morph. The critical test of atypicality bias was the network's response to the morph vector. When the 3 typical atypical morph vectors were presented to the network, stronger activation was produced in the atypical phase unit than on the typical phase output unit. Consistent with that empirical finding, the neural network showed a bias for atypical representations over typical representations. The simulation demonstrates that neural network recognition is sensitive to distribution of representations in the similarity space. These findings provide computational support for the claim that recognition is determined by the match between the input and the associated output, and the density of the surrounding representations. Bartlett and Tamanka extended the predictions of an attractor network model using real female face images. In their simulation, a 1,000-dimensional Hopfield network were trained on 32 patterns, consisting of Gabo filter outputs for 8 atypical faces and 8 atypical faces, and their mirror reversed images. It's an interesting experiment. The network was tested by presenting the image representation of 32 females, 50-50 morph faces, 16 combination of 4 typical and 4 atypical faces, plus mirror reversed images. The sustained activity patterns for each of the morph images was compared to that for its 2 parent images. The simulation results show that the morphed face fell into the basin of attraction for the atypical parent face 6 times, whereas it never fell into the basin of attraction for the typical parent face. The remaining 26 morph faces settled to a distinct pattern of sustained activity that differ from both parents. Of these, 22 were closer to the atypical than the typical parent. 2 were equidistant, and 2 were closer to the typical than atypical parent. Overall, the attractor network would have selected the atypical parent 87.5% of the time based on Euclidean best distance of the sustained activity patterns to the parent patterns. The attractor network model with real phase images exhibited an atypicality bias in the sustained activity patterns for the more phases. So let's go to information maximization hypothesis. Although, as several computational models demonstrated, an atypicality bias, the most parsimonious account is provided by information maximization. This account reduces the model to a simple goal of optimizing information transfer in sensory coding given to the statistics of phase images in the visual environment. The information maximization account is compatible with Krumm-Hansen's distance density hypothesis and generalizes this idea to a computational principle from information theory. Although the backpropagation model illustrated the general concept that an atypicality bias can emerge from the statistics of the training data, information maximization is an unsupervised learning strategy that is more biologically plausible model of learning in the brain. Information maximization also provides a more parsimonious account than the attractor network model, which assumes that coding takes the form of sustained patterns of activity and can take many iterations to settle. Moreover, in a hope-filled attractor network, decorrelation is a component of the learning rule that is necessary in order to encode highly similar patterns, i.e. phases, as distinct patterns of sustained activity. Decorrelation is closely related to the information maximization, and hence the atypicality bias that emerged in the attractor network could be related to the underlying principle of information maximization. Information maximization is a principle from information theory, describing a coding strategy for maximizing the information transfer capacity of a communication system by ensuring that all response levels are used with equal frequency. More response levels are allocated for high probability ranges of the input signal, and fewer response levels are allocated for low probability ranges of the input signal. In a system with limited dynamic range, information transfer is maximized by matching the response function to the cumulative probability density of the input signal. This concept is illustrated in figure 6. Adapted from Laughlin. The upper curve, as you saw, shows a probability density function for the magnitude of a stimulus property in the world, such as contrast level. The lower curve shows the response function that implements the information maximization strategy. In this example, the output has 10 response states corresponding to 10 just noticeable differences, so-called J and D, in response. The response function ensures that the interval between each response level encompasses an equal area under the probability distribution for the stimulus property, so that each state is used with equal frequency. In the limit where the states are vanishingly small, this response function corresponds to the cumulative probability function for stimulus intensities, which is the probability that the stimulus take on value x or less. Note that the slope is steep where the probability density is high and shallow where the probability density is low. As a consequence, equal changes in stimulus intensity have different effects on the response. The slope of the response function is given by the probability of the stimulus, which can lead to a number of perceptual effects, all stemming from a basic sensory coding goal of optimal information transfer. A body of research in computational neuroscience explores how information maximization may be central principle in sensory coding early in the visual system. For example, Laughlin showed that luminescence contrast coding in the blowfly visual system is consistent with information maximization, where the cumulative probability density of contrast in the blowfly environment predicted depolarization of a class of cells. These principles may be relevant to how we think about perceptual coding in higher visual processes, such as face recognition as well. Perceptual responses as revealed by similarity measures and GND was just noticeable differences, may be influenced by information maximization in sensory coding. For example, face discrimination is superior for same race than other race faces, which is consistent with a perceptual transfer function that is steeper for face properties in high density portion of the distribution in an individual's perceptual experience, i.e. same race faces, than for face properties in the low density portion of the distribution, other race faces, in parentheses of course. These concepts are also explored in Webster-McLeod 2011. Here we show how the information maximization principle of optimal perceptual coding would account for face typicality effects, and in particular the atypicality bias. We begin with the assumption of a typical face-off from high-density regions of the probability distribution for a set of physical characteristics, and that atypical faces have a characteristics with low probability on at least some dimensions, as illustrated in figure 7a. We'll take 7b there as well. Adapted transfer function and perceptual response. For example, a particular physical characteristics might be distance between the eyes. Figure 7b, as I just shown, illustrates the shape of the perceptual response function under the information maximization principle. In our example, this response function could be just noticeable difference for facial identity as a function of interocular distance, that is, distance in the eye. The typical face is mapped to a region of the response function that is steep, and the typical face is mapped to a region of the response function that is shallow. Due to the shape of the response function, the physical 50% morph between the typical and atypical phase is projected closer to the atypical parent in the perceptual response, as shown by the dashed line onto y-axis. I think this goes to show that similarity and difference are incredibly complicated things, and the lack of complexity we find within the educational system makes for no knowledge, non-understanding. It is just too coarse, it's too sloppy. It's like saying, instead of describing how you play football, just to say that there are two teams, and then you ask how do they play? They play against each other. What do you mean? Well, they are enemies to each other, and so forth. They wear different clothes, and so forth. This is educational system, what it's doing to human beings today, and it's taking away the chance of any knowledge whatsoever, but at the very same time giving them a sort of a dash or a smell or a pleasant odor of knowledge, the air of knowledge. You can be sure once you finish an education you will be very brown-nosed, toffee-nosed, but you will not have knowledge. And then you lost two things in one go. You lost your ability to learn, which can only start as you are a beginning. I think this shows this very clearly. And the second is you need to redo the whole thing. You need to start from the beginning. There's no way of starting where you are at and with that confidence you already have. Of course, you shouldn't go in with this without confidence, but it shows that you might not have the knowledge that is needed to go further to make an understanding of the world. And that understanding cannot be summoned in a few sentences. You really need to go into the detail. And this is very close reading in a deconstructed manner, just like Derrida did, by a couple of scientists who've done research and done it very carefully. Of course, the visual patterns with typicality and atypicality refers also to sound. Our hearing of P versus T and so forth takes similarity and difference as its goal. And also there you have a sort of deepening of knowledge. And I think there also was in the mid-section, just at the end of the former lecture, a typing error, because I mentioned non-Euclidean space. That never came up in this paper, but I think that would further the complications even more and make them even more interesting, because there is a real world out there, but terming that real world for the world at large, it is putting the whole thing to shame. It is shaming the world and shaming our human inheritance as being in the possession of faculties that makes it possible for us to understand the world. It is putting those faculties in shame, disregard them, not using them. And we get stuck because our mental energy is not sufficient to go out of the hole that we happen to fall into. I am quite certain now, and I'm also quite certain that, for instance, psychologists are just destroying more than they're producing. It doesn't matter what opinion they have, that's not what I mean. I mean that their method is just too coarse. It is like hacking all of our understanding with a hacksaw. And please remember, until the late 70s, mid 80s, we still perform lobotomy. That is putting in a dagger into the brain of the subject, thereby curing. This is the level of detail, the level of intellectual shape we handle our most precious things, our human soul. That shows that Western tradition is absolutely blunt to all finer details. And technology, although it's incredibly advanced, is nothing as advanced as the human intellect could be. And by mimicking technology, we make actually human intellect to become much less complicated than technology. Isn't that incredible? We actually devaluing our own intellect. Our abstraction capacity and everything is being devalued as we speak. Ian McKilcris is absolutely right. It is an apocalypse, but I think, in contrast to Ian McKilcris, I think this can be avoided from all different aspects. And you don't have to just point in some direction and say we need to go to the right brain. You can actually explain how the mistake started and what to do to cure it, to take it away. Understanding is the first start. Getting a bit humble and thinking that we don't really know so much. That position lets you start over again and actually go into the densities of knowledge. Because if you're stuck in a preemptive attitude towards the world, you lock that position. You lock the door to your own inner self and greater knowledge. And see how interesting, it's just marvelous. The complexity level doesn't have a limit. We are constantly engaged in the world with our intellect, and the world gets as real, as true, and as shared as the depth we put into it. And there Ian McKilcris has an absolute point. We know now by research, it's immense in the matter of things, that we don't have access to a communal world. And when people use common words, they don't refer to the same thing. There is no collective understanding anymore of common things, communally shared things. And that's the main part of Ian McKilcris' matter of things. Please do read it when you have the time. I think that's about it today. I say thank you very much, and I wish you a very pleasant afternoon. And now I'm going to put you through the panoramic view of this lovely setting we have here. Isn't it beautiful? And be happy that you're born after 1727, and that you are born. Should especially be happy that you're born after 1927, because then we have the chance of changing everything to the positive.